And please give Brian a round of applause to start with.
Thank you for inviting me here. I must say I like this weather much more. I'm from Chicago, and I left last week, and it was negative 10 degrees Fahrenheit outside when I headed out. You could boil water, take it outside, you'd throw it in the air, and it would freeze before it hit the ground. Mighty chilly, but so I'm glad to be here, glad to be giving this talk. I plan to talk about implied volatility using Python's Panda package or Python library. So who here uses Python or Panda? Okay, Python first, Pandas next. Okay, NumPy, take it. Okay, great. So I plan to cover a brief view of Python, why it's important, I guess. Go to the next slide. Talk a little bit about Pandas, and then cover the implied volatility. So I guess starting off with a motivation of kind of where this talk came from. I am in a MSc program, a Master's of Finance, and I learned about implied volatility throughout courses. And they said, you can go take some options prices, you compute the Black-Scholes implied volatility, and you'll see these nice skews and smiles. And I'm like, wow, that's really neat that you can actually kind of go to the market and compute this calculation, you'll see these different curves. I'm like, okay, I have to do this for myself. So what I did was I Googled where can I find free market data. I said, oh, I can go to the Chicago Board of Options Exchange. They supply market, you just put in any symbol you want. So you put in Apple, it gives you a CSV file of Apple options data. I was like, okay, how am I going to get this into the form that I want, right? How can I manipulate it in certain ways such that I can parse out the expiration dates, I can parse out this and that. And I realized that the key to doing this was Python and the Pandas package. And so that's kind of where this talk came from and the motivation behind it. So first starting off, Python. What is it? It's a dynamically typed language. It uses white spaces as opposed to brackets for control statements. So if you have an if statement, you have to have a certain number of spaces or a tab between each statement. It's grown in popularity over the years. So this is the programming language. You're looking at the ranks over the course of time. So 1999, it was the 22nd most popular language. Up to 2009, it was the 6th most popular. Now it's dropped down to the 8th. So people have been it's been growing over time in popularity because they realize that there are these nice packages, there's nice things you can do with it. So, and if at any time you have any questions, please raise your hand, stop me, shout Brian, I want to know about this. So, a couple of reasons on why using Python. It's cheap, obviously it's free, easy to use, and it's powerful. And we'll talk and we'll kind of show about why it's powerful later on in our presentation. And then I saw a nice kind of quote, why use Python over, say, R or some mathematical language? I would rather do math in a programming language than programming in a math language. I read that on a blog somewhere. I don't have the link to the blog, but it's someone who does technical consulting, and I thought that was really neat, that he'd rather do math in Python than say doing programming in something like R or MATLAB. So I really like that quote. I want to share it. Okay. Python. So what Python has, it has many built-in powerful packages. We'll review some of them. It has object-oriented programming. You have classes, you have base and derived classes. So you can create, say, some sort of animal object. You can create a dog and a cat. You can say the dog can bark, the cat can bark, or the cat can meow. And it has plotting. And that was kind of one of my key reasons for using this in implied volatility. You can easily plot it as opposed to something like C++. You have to go to maybe GNU plot or something else. So what Python does not have, it doesn't have overloading operators. So if you, say, declare a function once, you can't declare a separate function with different arguments. So I can't accept multiple arguments there. Multiple constructors. Speed, I guess, this kind of depends on what you're doing. It depends on what your definition of speed is. If you're a high frequency trader, you may not want to use, something like C++ or Java, but if you want, say, if you have an algorithm that you think is going to work for high frequency trading, I think one of the quicker ways to program that up is to actually write it in Python first, see if it works, and then if it works, maybe you go to Python, you go to C for production. So maybe prototyping in Python, going to C, yes.
So does it make much sense to talk about the speed of a programming language? Shouldn't we rather talk about the speed of its implementations? So for Python, you have projects like PyPy, and so you can write your code in Python, and then essentially compile it, which provides a speed up of about 5 to 6 times.
Okay.
So I think when you talk about speed, it should be tied to which implementation of Python you're using.
Which implementation, what you're doing, I think. Because I don't know if Python could rival something like C for speed at all, if you're, depending on how you program it up.
Well, but it interlinks so nicely with C that you can get all the C you want.
Yeah.
Just write it in Scifi, and if you really need to speed up,
exactly.
It's fairly easy to integrate everything.
Yeah.
Back to operator overloading. What operators are you talking about? Because obviously you can overload something.
I'm not familiar with operator overloading in Python. Maybe you can show me afterward on how that works. So that would be great. Doesn't really have pointers. We'll see a slight counterexample of that later on. But anything else that it doesn't have, throwing it out to you. Anything else that you would like in Python that you kind of don't have currently, or
protected variables.
Variables. Okay.
Protected variables. Like the fact that privacy is kind of emulate real. Be nice to.
Anything else? Okay. Let's see. So one of the reasons it's grown in popularity over the years is that sort of these nice with NumPy, you can have these nice containers. Essentially, you have arrays, you have matrices that you can do fast linear algebra. So if you have a NumPy array, you can multiply by another NumPy array. You can do some dot products via NumPy.linear algebra. You can do some eigenvalues. There's NumPy.linear algebra.eigenvalues. And if you actually look at the source code of that, you have LAPACK and BLAS behind it. So you have these fast C and Fortran implementations behind the scenes that you don't see, but they're there just to help you out and do the computations that much faster. Another popular package, Scipy. So this is for doing maybe scientific computing. It has special functions, integration, optimization, interpolation. And if you look at a lot of the source code of these, it's like minpack, so quadpack, a lot of open source functions that are actually in C and Fortran are the base. And I have to mention we have also a NAG for Pi implementation. So the NAG library is available for Python as well, about 1,600 functions. And it's built on top of our C library documentation and then 25 example programs. So as it's grown in popularity over the years, we've come up with these wrappers around our C library that will help users call. And we went to a lot of the banks the past couple of days and last month. We said, we have these wrappers. Do you want them? Do you like them? And they said, yeah, this is neat. We asked, what are you going to do with them? And a lot of them were going to do production code in C, but we're going to do a lot of the testing out in Python is what we found. They find it's a very simple and easy language just to test a strategy. So.
What's a common argument you hear in most discussions against using Python in production? What do people usually say?
It's mainly speed, a lot of it. So. Okay, so hopefully we're into something new that people haven't quite seen so much. So Python has this package for data analysis. It's called Pandas, and it's has many nice built-in functions. It's built on top of, say, numpy and scipy, so you can use these linear algebra features. So you have these common containers for holding data, a series data frame. So if anyone who codes in R, that may look familiar, the data frame, how you can store this object. It has a lot of nice functionality for reading and writing CSVs, indexing and missing data. So when I downloaded all this implied volatility data off the web, it's free, so it's not going to be perfect. There's going to be lots of errors, something like this. And it turns out Pandas handles that very well, just to deal with that. If there's not a value, there's a nan, as opposed to if I were to import that and say something like C, it might throw some sort of error while reading it. And then it has a lot of common time series functionality. So I guess before we go into implied volatility, I'd just like to do some maybe examples in Python so you can declare. Here I've imported a lot of the functions I'm going to use, so numpy, pandas. I'm going to use these later for the implied volatility curves, and then these cumulative months. That's going to be able to deal with the implied volatility data. So it's basically days from January 1st. That's what it is. So the end of February is 57 days from January 1st of the year. So in Python, you can declare an array. An array equals, say, numpy dot array. Thank you. Appreciate that. So we'll say it's 1, 2, 3, 4, 5, 6, 7, 8. So we'll have a three-dimensional array. And we can also do we'll look at that. So now our array is there. And you can do from numpy, say, dot linear algebra. We will import the eigenvalues. And then we can just do EIG of an array. And just like that, I have the eigenvalues and, in fact, the eigenvectors too. So you can see why this can be very appealing. You just import it and use it like that. You can also look at the documentation. The documentation is also behind the scenes, and you look where the function comes from and what are the input outputs. So that's numpy. If you actually look at pandas, we'll say a data frame is going to be pandas dot data frame of an array. So we'll take that array, three-dimensional array, and we'll turn it into a data frame, and we'll specify the columns as well. So the columns, we'll name them, let's say, 1, 2, 3. So those are the column names. And then you can look at, say, data frame. You can look at the first column. Let's print the data frame first. So here, you have the data frame, you have the columns, 1, 2, 3, rows. You can also specify indices. We're not going to worry about that for now. But Pandas has these nice things that you can do. So you can print dataframe.1 if you just want the first column. Or if you want dataframe.2, you can just look at the second column. Another thing you can do is you can add dataframe.1 plus dataframe.2. So if you want to add two columns together, you can easily do that. Let me show you. So let me get the original data frame. So there's the original data frame. And if you want to add two columns together, it automatically knows how to do that. Right? Maybe you want to add a scalar to a column. It takes care of that without any work for you. Right? So here you have a vector, you're adding a scalar, and it automatically knows what to do. Another thing you can look at is, say, dataframe.describe. You can look at features of what's going on. So let me scroll down. So it gives you basic statistics, but these can be played with around. If you want different quantiles, you can look at that. You have the 25th percentile, 50th, 75th, max, min. So you can see a lot of the times if you're dealing with, say, a lot of data, maybe you have time series data coming in, and you want basic statistics, you can easily store it in a data frame and play around with it. Another thing I didn't realize is that what a data frame is actually, it's a pointer. I had no idea. Well, you can think of it as a pointer. If you look at data frame, if you want to change, say, the 0th elements, I need to go .1. So if I want to set that equal to 100, and now let's print the original array. The original array changed. So, and the same thing, if you change an array, the data frame will change as well. So let's do something rather interesting rather than saying, look at this simple 3x3 case. Let's do some random data. We're going to store that in a data frame. Let's see. And let's just make it numpy.random. And we'll make it, say, 1000 by 10. And there it is, and so let's print it too. Print. So there we have 1000 by 10, so you have 10 columns, 1000 rows, and looking at that, just look at the 0th element. There's our randomly distributed, our random numbers. And you can do some interesting things. You can say, okay, I only want that where the first column is greater than, say, 0.5. And similar to MATLAB, it returns this true false array. And then you can also, if you want the whole data, what you do is you can kind of cast it such that, okay, I'll take it the whole data set, only where the first column is greater than 0.5, I want all those data, all those kind of data points, all those rows. So you can do that, and then if you look at, say, the first column, let's see, you should see all those rows are greater than 0.5. Second column, just the rest of the rows. So. Questions so far? Hopefully not. Pretty good.
That's kind of a long way away from 500.
That's a long way away from 500. It is, but the indices are different.
Well, I'm saying did it say 451?
Did it say 451?
It's down the bottom.
Yes. It does. Let's see. So they're all different. I have to look at why that is.
Generally, it's the random data every time.
Half of them is not exactly half of them, but just like a binomial distribution around.
Okay. Yes. Thank you.
1000 rows. So that really makes sense. It's like just.
Okay. Thanks. And you can also do that .describe if you want as well. And then just these are data frame of just different statistics about each row. So remember, here we took out where the first row was greater than 0.5. So you take out everything that's less than 0.5, so you have everything between 0.5 and 1, so that mean is going to be 0.75. So it should make sense. The world works for now. So. Okay, so that was. Oh, can I have this? Okay, so now maybe you have these time series data. Something else you can do is you can do this data range in Pandas, where you specify a start time and you specify an end time, and maybe some sort of frequency. So here, can't really scroll, but I think the frequency was every minute or so. And then it'll produce this index of times every minute. Here I chose, when the market opens and when the market closes. And then I'm feeding that into, say, just a random numbers for every data. So you can look at here the data frame. So we have 391 values, and you can look at, say, if one stock is Apple. Maybe these are the Apple returns or Apple price. Obviously not the prices, but you can look at something over every minute. So it opens at this, and then you can go from down the list. And some neat things you can do is you can resample that. So this is called dataframe.resample. And maybe you want to look at, say, every 5 minutes instead of every minute. And how do you want to resample that? Well, maybe you want to look at the mean of every 5-minute intervals. You can do how, every mean, and then let's print. We'll print this then. Let's look at the first column. So now from every minute, you have every 5 minutes going down the list. So that's specified by your how function, how you want to do that. So obviously there's the built-in function mean, but any other built-in functions you can specify as well. So saying you want to specify, I think I've created this, every other element. So I define my own function where it takes an input of a series and it's going to input every other element. So for I in this range from 0 to n, going every second, just add this running sum, and I've specified my own, and you can do the same thing. Yeah?
So if we're doing this with financial data,
Mm-hmm.
and we don't want to look into the future, can we do that with a similar command here? So when we take the mean, I guess we're leaking data in from the future minutes and kind of backwards, aren't we?
Yes.
Is there a way we can modify it so that it's kind of the mean of the last 5, say?
Choose by one, right?
Yeah. I'm not sure because your array is changing every minute, but I haven't seen it, but I'm sure I can.
You can just shift. You can do .shift 1. It's going to shift back everything in cause of.
Oh.
There might be a keyword argument also that lets you specify forward or back or forward.
Okay. Good. Yeah. Okay. Very good. So that. Go back to our PowerPoint. So that was kind of the basic intro to numpy, pandas, scipy. Let's go to implied volatility. So this is the Black-Scholes formula. It's a basic function of 6 variables. Here, S0, KT, sigma, RD. So you have your underlying price, strike price, time to maturity. You have some volatility, your interest rate, and then if the stock pays any dividends. And these are up here in the formula. And so implied volatility is, well, some of these variables we can actually observe in the market. So for example, the initial price, that's wherever the stock is today. We can see that in the market, and I can buy a stock for, say, $500. The strike price, well, that's specified in the contract, right? If you were going to buy an options contract, there's a specific price that you can exercise it at. The time obviously specified in the contract. The risk-free rate is a little bit harder to find, and the dividends they're specified by the stock as well. And so, actually what you can do is you can observe these red variables in the market. So, for a certain contract, these are fixed, And R I'm assuming to be 0, but you can specify your own interest rate. And then you can actually buy a contract for a certain price on, say, the CBOE or anywhere else. So what you can do is you can actually play with this sigma a little bit, because sigma is from this equation here. So this call contract is going to move up or down depending on what your volatility is, what your sigma. So you can play with your sigma and find where is this Black-Scholes price, the equation in the before slide, equal to the current market price. And it ends up to be finding a root of an equation, right? You're just finding this root where it is this equals certain price. Most of these are fixed except in here. So it's just your root finding. You do have a derivative, but we'll talk about that later in a bit. And so you should ask yourself, does this implied volatility exist? It turns out it does, because if you look at, so as sigma goes to 0, as the volatility of the stock goes to 0, what you have is really only it's going to be affected in here, and those in turn are going to go in here. But as volatility goes to 0, you have two terms. One is 1 over sigma, one is sigma. And so the sigma goes to 0, but 1 over sigma is going to go to infinity. So you have d1 and d2 both go to infinity. As they go to infinity, your standard normal CDF, that one actually thinks it's the CDF. Yeah. So this goes to 1, this goes to 1, so you get your strike minus spot discounted. And then it turns out, as sigma goes to infinity, what you have is, so d1 and d2 are going to be different. As sigma goes to plus infinity for d1, this is going to be positive, so this will actually go to positive infinity. And as this goes to positive infinity, this is going to go to 1 again, so here you just get S0. And for d2, it goes to, you have a negative sign here, and this sigma squared is going to dominate, so sigma goes to positive infinity, d2 is going to go to negative infinity, this goes to 0, and so you just get S0. So it turns out this Black-Scholes formula, it's a monotonic function of sigma. So you can actually find a root for it. So let's go to the examples. First, maybe we should look at the data. So the data that we can actually read in, this is what you get from the CBOE for every stock. It's going to have some sort of header file, and then each row is going to be a different option. So you can see here's actually what the options, what the columns are. These are the calls. These are the puts. You have last price. There's ask, bid, volume. So when I saw this, I decided that, okay, the easiest way to read this in would be Pandas. I'm going to work with that. So let's read that in. So this script is basically going to read in the header file. It's going to just open it. It'll read the first and second lines. If you will look at the header file or the header, basically what you have is you have the date, you have the basic stock symbol. Here this was taken October 4th, 2013. So we're going to need that for computing our implied volatilities, because if it's October 4th, we need to know how many days it is until October 3rd or 13th for the time. So we're going to need some of that information contained in the top to compute the implied volatilities as we go. Okay, so let's read that in. Okay, and then here's actually reading in the whole file. So I'm going to save it as quote data, and you have this pandas.iro.readit. You just specify what's the separator, which one's the header. So in this case, it was our second line, was the header. What to do with NA values, And then here we're just filling the NA values with 0. Okay, so it's read in, and let me, let's take a look at what actually we have. So let's print quote data. So there is actually our, we just read in 22,000 options prices. There are calls and puts. So these are the calls, these are the puts. It automatically recognized, so last sale was a repeated column index. So Pandas automatically recognized that and put a .1 at the end, just so there's no confusion. So that when I go, say Pandas quote data .ask, it knows which ask I'm talking about. In this case, it's the calls ask price. And then if I do quote data .ask.1, it's of course going to throw an error. You can just change that. So then these are the puts ask price as well. Okay. So let's look at the data again. Let's look at quote data.calls. So this is the first column in our quote data file from the Chicago Board of Options Exchange. You have the expiration date, so this is the 13th of October, or I'm sorry, this is actually the year, 13 October is the month, and then it expires at the end of the month, so the 31st of October. And that's why we're going to use the cumulative month in the very beginning. If you remember, that's the number of days till the end of the year from January 1st. This is the strike price, 355 all the way down to 730. I think Apple here is maybe around 450. And then this is the actual contract. And then we're gonna just make note that there are they end in different things. So just remember that as we go. So those are the calls. If you want to look at the puts, let's go look at puts. And then a very similar thing, just on the other side. It's for the same strike price. So now what we have is we have this data, but we need to get, essentially, to compute the implied volatility of our options, we need 1, the expiration, and 2, the strike price. The strike price and expiration are both in these first headings, right? They're in this calls and puts. So to do that, we can write actually a Pandas function to compute that. Before we do that, let's actually just get rid of some of the bad data. So one line of it, we're just going to get rid of everything if there's no last sale, so if there's no option at a certain price, let's get rid of it. And if there's no put option at a certain price, we'll get rid of it. So just trimming the data down so we don't have to compute the implied volatility at the end. Too many. So now if we print quote data, we've gone from 22,000 to about 16,000. Okay. Another thing you can do, it's kind of nice, is you can actually apply these functions to certain columns in Pandas. Right? So you can say apply this math.sign to the whole ask column. So if you remember, ask is a float for Python, and so I'm going to apply the assign function to the whole column. Right, kind of neat. Notice how these indices are different now. That's because we got rid of the data that are bad. So, questions at all, or? Okay. So to get the expiration, we're going to define these functions. Called get expiration and get the strike. Right. Basically, it's going to split whatever input it's taken. It's going to take whatever the month it is and the day. We're actually not using this. This will be for our program later, but don't worry about that for now. But basically, it converts whatever year it is to some int, multiplies it by 365, and then computes the time from January 1st. So basically all that's doing is it's taking this first column here, parsing this, and whichever these dates are, it's getting the number of days from January 1st. So let's do that. And then the second function here is just getting the strike price. So it's taking that column and splitting it, and then just returning whatever the second, I guess it's the third element is. So once we do that, we define these functions, and then we can actually get the expiration dates. So here, if you look at the expiration dates, so if you remember, we're looking at October. So October is 304 days from the beginning of the year. And that's how we have those for the start. And then the last ones are 1,126 days from January 1st of 2013. Okay. So, let's see. We do the same thing for the strike, and then we join them to the original data frame. So we're getting the strike price from that first column, and we're adding that to our data frame. So if you look at the data frame now, we have these two new columns, the expiration of the strike, for all of our options. Okay. And then you can also look at other functions. You can do quote data dot columns if you just want to get the columns of them. And so those are the names of all the columns. You can do a quote data dot head if you just want to look at the head of your data frame. Just to see what you have. Okay. So now the implied volatility. To do that, the first thing we do is we create these Pandas series that we're going to hold the implied volatility. So here I'm creating the implied volatility in a series, saying it's all zeros. The index is going to be the same as our current index, and I'm just calling it implied volatility call, and implied volatility puts be here. And here's where we're going to store the implied volatilities in these two frames. And then also, we have to change the expiration. So what we're going to do is we're going to take the current expiration, subtract off today. So remember, today's date is October 4th. We have options that expire at the end of the month. And so what we want to do is we want to subtract off the number of days to get the expiration date and divide by the number of days in a year. So let's do that. And then here's where the actual options pricing occurs at, or where the implied volatility pricing occurs. So I've created these functions. That was when I imported them. So I'm going to take the expiration, the strike, whatever the current underlying price is, and then bid and ask. We're just dividing by 2, so we'll take the price in the middle. What's going to return is that implied volatility. So here's where the root finding occurs, in this one and this one. Okay. So let's do that, and hopefully it'll work. I've got to wait for it. Okay. It looks like it worked. So here, so for some of these you get 0 for maybe you couldn't find, there was no root. Again, it could be the data. And so these are the implied volatility for the puts. Okay. Now it doesn't really, I mean you can see it in a list, but I think maybe graphing it would be much better. So let's graph it and see what we get. So this is the points. So for here, I'm taking actually, so remember we have a ton of expiration dates for our options. I'm just taking whatever the first expiration date is. So it's going to expire in, 29 days or something from our October date. And this is what we get for our implied volatility curves. So what do you notice? So first of all, there are a lot, maybe this is bad data, but also you get different curves. Does anyone know why that is?
guess you have the term structure as well.
So here you're only looking at one date though.
Oh, okay.
So yeah, this is just these options all expire in like 25 days.
Oh yeah.
But the different strikes.
They're the different strikes, yeah. So I'm sorry, the strikes are on bottom. These are the strike price. I didn't label this graph very well. And these are the implied volatilities. So why do we have different curves? Goes back to the data.
So it's to do with the
Prices.
prices at the end.
Sorry?
Prices must be different as well.
Price, yeah, so there's difference in prices, but why? I mean, you get these kind of, they're all along the same thing. So what's actually happened is, if you look at the data, it goes back to what these numbers mean. And it turns out those are the numbers on different exchanges, right? So every time you see this option, this symbol, it's going to be on the same exchange every time. And so that's where it happens.
And why is it different on the different exchanges?
I don't know. Good question.
Because it's a massive difference as well.
Yeah.
It's not,
Um,
I mean, if you come back to your plot, it's
yeah. There's one thing I left out. So remember I didn't have any dividends here, no interest rate. Right? But Apple actually it does have dividends. So one reason they could be slightly off is that reason as well. I would guess there's different dynamics of the contract that I don't know about, or that we don't know about in there. Okay, questions so far?
Can you remind me, what did you use for the rate?
0. So it's no interest rate, yeah.
So X is the price of the option that they pay at, right?
Yes, so these are the strike prices.
Around 500 we have the strike there. I guess that's the special point.
Yep. So this is maybe it's probably the current price. Yeah. So yeah, I guess I didn't explain how I was graphing very well. So yes, these are strike, implied volatility, you're finding the root, and then you're just graphing them. So what we can also look at is, so saying we don't want,
And those are calls, right?
these are calls, yes.
Are you doing that on mid prices, ask prices? What is
It's the mid price, it's bid plus ask over 2. So maybe instead of looking at, say, the first expiration date, we can look at the last expiration date. Just copy that. That's what we get for the last expiration date. So, slightly strange. Yeah. So what we've done is we've created actually a script to do all this, and then plot the implied volatilities. So let me do that now. So the script that I've actually created will do all that, and it'll show you the implied volatilities on one graph, and then it'll fit a volatility surface, which we'll discuss in a bit. So here the script is basically, it parses the data, it weeds out the bad data, finds the implied volatility, and it'll graph it for us. And this is all data taken from the CBOE. So I chose Apple here, but you can choose IBM, anything you want, and it'll say the same thing. I think the first thing to look at might be this. Implied volatility curves at different expiration dates. So here you have the closest expiration date and going further out to the end. So what do you notice? Anything strike you? No?
Well, I don't know. I mean, obviously the more sensible ones are the ones that just have a single curve.
Yeah.
Maybe the dividend is expected in October and is really ruining your implied vol using a simple Black-Scholes model.
Could be.
I mean, it's silly that you can have a range of 15 to 40%.
Have you got some...
At the kind of...
Yeah, so these, actually, I talked to someone about this, and he said that they're not very liquid in here is why you get this high volatilities. So, a guy, he trades these options, he trades off the volatility curves. He said, these are absolutely useless, you just throw them out right away, you don't trade them at all.
Yeah, I mean, options that have very small prices are kind of incredibly susceptible.
Yeah.
And so basically you should split it into two, and you should take puts for half of them and calls for the other half of the curve, depending on whether they're in or out of the money. So that means you kind of throw away a fair amount of the prices.
Yes, I agree. Other things to notice? Yes.
Can I just ask, you have a variety of different exchange traded contracts. Have you been very clear about which ones are European style and which ones are American style?
I have not.
Yeah.
That may be why the different curves as well.
Did you make sure that you have bid ask for in every situation to calculate the need, or some when you do that initial field you put 0 and for the missing data?
Yes.
Maybe you calculate the mid with one of the values is 0. Maybe this is
Oh.
way of explaining.
I did not.
40% or 10%. Excuse me.
Yeah, I did not look at that as well. Also, I showed this to someone today, and he said that normally these curves should align if you're trading these. Is that true, false? Is that... Yes, I see some nods, so something's amiss, but I think the thing to take away is, you know, you have this powerful package of Python and Pandas that you can kind of do your own work with. Like, this took me maybe a day to put together, but I think it's kind of a neat demo to show. And you can put all these implied volatilities curves off of free data available to you. So something else you can look at is the implied volatility surface. So here I think I'm fitting I think it's a cubic polynomial here in both the strike and days to expiration direction. Am I over time or how's that?
It's fine.
Okay.
It's fine.
So you can fit a cubic polynomial to this, and that's what the option trader I spoke to. He was fitting quadratics in this direction, obviously cutting off the initial wings, and then trading off that. So before I talk about fitting polynomials, we can also look at this graph as well. And these are just the points plotted, as you can see. We should have 8 expirations, so 1, 2, 3, 4, 5, 6, 7, 8. With 8 expirations. That's essentially the point you're fitting to. Okay, let's go back to this. So I already talked about the different implied volatility curves. So these are what the symbols mean off the CBOE website.
But kind of just reinforcing Ian's point, if they were all the same, there'd be no point in having all the contracts. So the contracts must have some differences, some of which may be subtle, some of which may be not so subtle.
Absolutely.
But it is a consolidated tape, right? So it's just bringing all. It could be meaningful shares. You have exactly the same share, listing 10, 20 different. I think this would make sense having in the same contract as well. I mean, I'm not familiar specifically with this market, but
Yeah, equities, you would trade the same ticker on several exchanges. So these feel like VCNs in equities.
I'm sorry?
So these feel like different exchanges in equities, whereas but you would still trade the same contract in different exchanges.
Okay.
Yeah, but in
Pandas
equities,
is still.
like this looks substantial enough to be auditable. I mean, if that was the case, right, it wouldn't be there. So, like in equities, I know it wouldn't observe any difference of that scale.
But this data problem is clear.
I'm not familiar enough with the finance to comment. So, sorry.
Well, I guess one thing also is they might not be sampled at exactly the same time as well. If you have some very liquid options, maybe that quote got sampled earlier than at different times. That could be one explanation as well.
Illiquid prices.
Yeah.
What is the probability that all the contracts for January expire on the 31st of January for each of those exchanges?
I haven't looked at that yet.
I'd be amazed. I'd be really surprised if that was the case.
Okay. Yeah, I guess I just assumed they all expire at the end of the month, but
That's not possible.
So different reasons for skews and smiles. People have different risk preferences. So you may be afraid of a large swing in a price, a large drop. So maybe want to pay more for options that with a lower strike price. And then the fat tail distributions. So Black-Scholes assumes you have a log normal, but in practice you have these fatter tails. Then I also looked at timings. I will hurry up. So timings, so different timings in Python. fsolve is a function from Scipy. So basically you have Python, Black-Scholes. That takes actually 180 seconds. If you do all the implied volatilities in Python. Just with the callback, it takes a while.
So what's the scale of the inputs again?
Scale at 30,000 implied volatilities. Each one takes about 10 iterations to the callback. You're calling a cumulative normal distribution function, you're calling an exponential. So. Instead, you go to fsolve and a NAG Black-Scholes function. It takes about 15 seconds. Just with taking all the computation here out of Python. So still using fsolve to find the root, but instead using a NAG Black-Scholes, 15 seconds. NAG for pi, so if instead you use one of our root finders, you get about a 66% speed up. And then NAG-C only takes about 0.29 seconds. So if you build a shareable library and you set pointers to the data, so if you point to say this is where all the strike, the time, the expiration, if you just point to that and point, here's where I want the data, you do all the hard work in C, it takes under a second. And I can show you that now.
Excuse me?
Yeah.
Sorry, what's the difference between the second one and the third one that you had there?
Let's see. Here, this fsolve is in Python.
Yeah.
And here we're using a NAG root finder.
Well, both of them are calling it from Python, right?
Yep, both are calling from Python. So here, they're both callbacks are in Python.
The NAG root finder and NAG for pi is in C, right? Already on the C side.
So yes, it is in C.
So the root finder is in C and the Black-Scholes model is also in C.
But
why is there such a big difference between NAG for pi and NAG C then?
But you're calling them from Python is what it is. So.
Are you running like a for loop?
Yeah, it's the loop in Python. Yes.
To root find.
That's what you're doing.
A really interesting use case would be to look at the pure Python implementation using Scifi, which probably is going to take 15 minutes. That's going to write QC code optimized.
Yeah, that would be. Yeah, I agree with that. Pretty good.
So for the third one, does it call NAG for pi for every option.
Yep, it does.
Yeah, I was going to say that's the other thing that's kind of crazy that you've done here. That you've got basically 30,000 highly correlated problems, and you're treating them as if they're a completely new problem. Because my guess is the fsolve is just going to use the same initial value, whereas in fact a much better initial value is the last solution you've just found,
Yes.
for instance.
Yes, so that's some, yeah. You can do that. I see what you mean. And then derivatives. So none of these functions use derivatives, but we have derivative. We have Vega. So I would expect you can get better timings for these if you use that in the root finding process. And then one last thing about fitting polynomials. So in our script we fit cubics in the strike and time to expiration direction, or if we try different values. So here we're fitting 6th degree polynomials in both the x and y direction. See what we get. Let's take a while. Not like these. There you go. You get something crazy.
Can you rotate it?
Okay, I see. So essentially, you're overfitting your data. What's going on? So while it was good to fit cubics, not so much to fit those. Essentially, yes, they're going to. This is going to agree more on the points, but in between, you have no control over how the function behaves. So that's why you have to be careful when you're fitting these graphs to points. And to show that, I have this little script. So this script is going to fit different degrees of polynomials to this data. So if you're looking at, say, one strike price at different dates, you're going to have a higher strike, when there's closer to expiration, and then it may level off as it goes. So if you fit a line, and here you're doing it in the L1 sense, so you're just taking the difference. If you instead fit a quadratic, you get that. If you fit a cubic, with this, 4th degree, that. 5th degree looks even better. 6th degree, you get these big jumps. So, yes, you get better fits in here, here, here. But then you have that for the between those dates. And then again, same thing happens if you fit 6th, 7th. So what might be a better fit to these points? Any ideas? Well, we can do a cubic spline. Try that. So here, you're fitting these cubic polynomials with knots in between every point. So either cubic or quadratic. I think it's cubic. And that's to keep it nice and smooth. So something else you can do is if you don't want to fit a cubic spline, you can actually fit another cubic spline that's monotonic between points. So you notice here that you go up a little bit to get back down to that point. Maybe you want a monotonic polynomial, so it'll only increase, but it won't go beyond that and start heading down. So that's an idea. Okay. And I think that's some poor results we can do better. Fitting some sort of different curve. That's all I had. Any questions?
Any questions?
So I have a question about, so when you were doing the root finding on the whole series of your applied volatilities, so now even in your example on the notebook, you had a for loop of NAG calls.
Yes.
So it's sequential.
Yes.
So the simple question is, what's the easiest way to put it on an octa-core in parallel? Because in this way you can simply ask for implied vols 8 at a time. With Python or a NAG side.
There is parallel programming in Python. I don't remember the exact package. I didn't even know it off the top of my head. I'm sorry?
There's a parallel engine I think you can use.
Yeah.
You can use some PDI, so there's a PI if you want to be controlling.
Yeah. So yeah, there is. I haven't done it, but yes, that would be a nice next step.
Any further questions?
On your benchmark, I think was, you tried different solvers to NAG1 and the F solver. Did you compare number of iterations that were required to get to your root?
I did not compare that.
Looking into it, I mean, the speed up might also be that maybe the NAG1 is, gets there quicker. Or,
yeah.
So I think like if you have a benchmark, I mean, that's one of the parameters that you should also compare more than just speed.
Yeah.
Purely is number of iterations, precision, I guess. But still.
Well, I guess if there are no further questions, then I guess just want to give Brian a round of applause. So I spent many an hour doing a time series library in Java, so now I have to waste the time. So thanks for telling me that anyway. So I definitely have a look at it. So please give Brian a round of applause. And also please come to our next talk as well, the panel that I mentioned, the marketing. So